Welcome back. In this video, we'll be starting section 3.4 on integrals of trigonometric powers. All right, so the goal is pretty specific, and so let's go over it. Use trigonometric identities and the techniques of integration from section 3.2, that's substitution, and 3.3, that's integration by part, to evaluate the integrals. All right, so the first type that we'll look at are products of sines and cosines. And then in the next section, we'll be looking at products of secants and tan. So secant K, tan M. All right, so what's nice about this is it's quite easy to spot. It's easy to see that you have one of this, and then the method will be quite specific, right? It's almost going to be a recipe. So let's start right away. We'll start with the integrals of type sine to the k, cosine to the m, just because we're more comfortable with sines and cosines than we are with secants and tangents. So we are going to need three different trig identities. So here are the trigonometric identities that we will use in this section. First one, cosine squared plus sine squared equals 1. Second, this one might be new. We saw it in the review, but I don't think you've seen it before. Cosine squared is 1 plus cosine 2x, so I'm doubling the angle, divided by 2. And sine squared is almost the same thing, but I'm going to put a minus instead of a plus. All right, so example 3.4.1. Consider the integral sine to the 5 cosine 25x dx. I want to evaluate I using the substitution u equals cosine of x. So I'm going to give you the substitution because this is the first example that we do like this. And once we've evaluated, I'm going to ask what about k and m made this substitution work so that we know when to apply this substitution. All right, so let's try. I have u equals cos of x. The derivative of cosine is minus sine of x dx. And so I'm going to replace dx by minus 1 over sine of x du. All right, the minus is going to come out, and then this sign will cancel with one of those, so I'll end up with 4. So I end up with minus sine to the 4 cosine 25x dx. Du. All right, to make the substitution complete, I need to rewrite everything I see in my integral in terms of u. This part is easy, it's u to the 25. All right, this is the part I'm going to need to work on. I want to use this identity. It relates sine squared to cosine and constant, so I'm going to say right here, this is sine squared of x squared. All right, sine squared, if I send this to the other side, I'll get that it's 1 minus cosine squared of x squared. And, well, cosine squared is u, so I get 1 minus u squared squared. And then let me expand it. I'll need to expand it anyway, so let me do it here. I'm going to do 1 minus 2u squared plus u4. If you remember the way to square binomial like this, just do it. If you don't, you could write it as 1 minus u squared times 1 minus u squared and expand. All right, so I'm getting minus 1 minus 2u squared plus u4, u to the 25 du. I have a product of polynomials. The easiest way of integrating this, do you remember? Yep, you distribute, you get one big polynomial, and then you could use a bunch of power rules. So I'm going to get minus u to the 25 minus 2u to the 27 plus u to the 29 dx. And then I'm almost done. I'll get u to the 26 over 26 minus 2u to the 28 over 28 plus u to the 30 over 30 plus c. All right, final step. This is the correct answer in terms of u. We want it in terms of x. And so I'm going to replace u by cos of x. So minus cos of x, sorry, look like random writing. So minus cos to the 26 of x over 26 plus cos to the 28 of x. I'm going to cancel the 2 with the 28 and get 14, and then minus cos to the 30x over 30. All right, I want to know for which values of k and m would this work. All right, so this is the important part right here. This is when I needed to be able to write whatever power is left as a power of sine squared. So I need this here to be even. All right, so 4 worked, 6 would have worked, but if I end up with 3 or which is sine, I can't do this right here. So we need this part to be even, this exponent. And so that means at this point, it would need to be odd, right? I have an extra 1 here that canceled. And so for this to work, we need an even number of sine at step, let me put, let's call it step 2, at step 2. And so an odd number of sines at the start. And so we need k needs to be odd. All right, so if k is odd, then this substitution would work. Let's try one where k is even. All right, so the first substitution doesn't work. I'm going to evaluate I using the substitution u equals sine. And then we'll do the same thing. We'll say, well, for which value of m and k would that work? So I'm going to take u equals sine. So du equals cos of x dx, or dx equals 1 over cos of x du. So the integral is sine to the 14 cosine to the 5 1 over cos of x du. This cos will cancel and I'll end up with 4 cosine. Need to write them in terms of sine. Well, since I have 4, I could write it as cosine squared squared. That's 1 minus sine squared squared. So it's 1 minus u squared squared. It's 1 minus 2u squared plus u4. All right, so the same idea is just that we're switching the roles of sines and cosines. And so here I get u to the 14, 1 minus 2u squared plus u4. I can expand. And so I get u to the 15 over 15 minus 2u to the 17 over 17 plus u to the 19 over 19 plus c. And so I get sine to the 15x minus 2 sine to the 17x plus sine to the 19x over 19 plus c. All right, so for which values of k and m would the substitution u equals cos of x work to evaluate the integral of sine kx cos mx? All right, so same thing as before. This is the pivotal point. In step 2, we need to have an even number of cosine. And so at the start, so I had one more, right? Because this one killed 1, so I had 5 turned into 4. So at the start, we need an odd number of cosines. So I need m to be odd. So if m is odd, the substitution u equals sines work. And we saw if k is odd, then u equals cosine work. So as soon as one of the two powers is odd, one of these substitution will work. If both are, both work. And so the only case that's left is if you have even powers. Right, so I want to show you one example, then we'll recap the method. All right, so example 3.4.3, evaluate the integral of cosine squared using the identity cosine squared equals 1 plus cos 2x over 2. All right, so that's the identity I gave you at the start. Let's see how this will help integrate cosine squared of x dx. Right, so I'm going to replace it all using the identity. And then I'm going to be able to split this. I'm going to get the integral of 1/2 plus the integral of cosine 2x over 2. Integral of 1/2, you could pull the 1/2 out, but you don't need to make it a separate step. I'm looking for something whose derivative is 1/2, so the easiest thing is 1/2 x. And then here I could pull the 1/2 out, and then the integral of cosine is sine, but because I have a 2, I'm going to need to divide by 2. All right, so this here is from our good old takeaway 1, the one that we keep using. Yeah, that's why I gave it a number. That's the only one that actually has a number so far. All right, plus, oh, sorry, not purple, plus c. All right, so what's nice is you go from something that's a product of two cosine, and products and exponents, it's hard to integrate them, and you turn it into something that's a sum and constants. The only hard part is that 2 inside, but that we know how to deal with because of takeaway 1. And so I get x over 2 plus sine 2x over 4 plus c. That is my answer. All right, so these identities, the more complicated one, and the same one for sine squared, which is 1 minus cos 2x over 2, those we'll use when we have an even number of sine, so 2, 4, and an even number of cosine. If one of them is odd, then the substitution is what will do. All right, so let's write this out. Method for evaluating cosine to the k, cosine to the k, sine to the m. If I have an odd number of signs, so if m is odd, wait, let me check just one thing. Yeah, they're backwards. I'm going to switch them. So here you'll see in your notes sine, cosine, because it matches what's above. Just notice the change. So if you have an odd number of signs, so if k is odd, you should use the substitution u equals cosine of x. So du will be minus sine of x dx. That will cancel one of the number of signs, and so what will be left will be sine to the k minus 1, and you'll use the fact that sine squared is 1 minus cos squared, so 1 minus u squared, to rewrite sine to the k minus 1. If you have an odd number of cosine, so that means m is odd, you use the substitution u equals sine of x with du is cos of x dx. You use that cosine squared is 1 minus sine squared of x to rewrite sine to the m minus 1. If both numbers are even, you replace all cosine and all sine using that cosine squared is 1 minus cos 2x divided by 2, and sine squared is 1 plus 1 minus cos 2x divided by 2. All right, so every time you apply it, you double the angle. You expand and separate the entire expression into integrals that look like this, and then you restart with each integral. All right, so let me show you on a harder example what case 3 will look like, because it's more involved, and the higher the power, the more complicated it becomes. All right, so let's try it with cosine to the 4. Cosine to the 4 is cos squared of x squared. So I'm going to use this identity to rewrite the interior. Now everything in my integral should be in terms of 2x. I'm going to expand and separate into integrals that look like this. So I'm going to expand, I'm going to get over 4, 1 plus 2 cos 2x plus cos squared of 2x. Don't be afraid of taking a bit more time here if you need to. It's not a race. Right? If you're not great at expanding, at foiling, just go at it slowly. All right, now I need to separate them into integrals. So I get 1/4. I get cosine 2x over 2. And I get cosine squared 2x over 4. All right, so this one, easy. This one, medium. This one, I still have a squared. I'm going to reapply the technique, so the third one is hard. All right, so here I get x over 4. This one, next one over, I get sine 2x. The takeaway tells me to divide by 2, so I get over 4. And then the final one is going to be the integral of, and then I apply the identity again, 1 plus cos over 2. I've pulled out the 1/4 in front. And then whatever angle you have, every time you apply the identity, you double it. So I'll get integral of cosine 4x dx. All right, so I'm getting x over 4 plus sine 2x over 4 plus, and then 1/4. Let me integrate it. You could split it first, but it's I'm running low on space, so 1/2 would give x over 2. And then the cosine for x over 2, cosine integrates to sine, so sine 4x. I had an over 2, I need an over 4 because of take away 1. All right, so let me simplify this if I can find, so let me move this up a bit. All right, so I'm getting x over 4 plus x over 8. That's 3x over 8. I have a sine 2x over 4. All right, so this one is taken care of. This one is here, and now I have this times this. So that's sine 4x, and then 4 times 2 times 4 is 32. All right.